So we left off, was that Saturday's session, looking at these three charts for the credit data set, comparing the models M0, M1 until MP. Quick reminder, M0 is the model, there's only one of them, that uses none of the predictor variable data available to us. The other extreme is MP, that uses all P predictor variables. And we do this for, well, that's your M0. Or maybe this is M1, but then where is M0, right? So number of predictors, we appear to start. Now either we're just consciously leaving it out from the chart, but this is M1, this is M2, M3, and what do we have on the vertical axis? Well, that's a square root of the BIC. We'll probably see how to calculate this in today's session. Another comparison between the models is what is known as the validation set error. And there's also the cross-validation error. And each time you pick the model, meaning you pick the number of predictors, that gives you the lowest value on the vertical axis. We can very quickly read this. For the credit data set, 3 quantities are displayed for the best model, containing D predictors, for D from 1 to 11. The overall best model based on each of these quantities is shown as a blue cross, and that's square root of BIC, validation set errors, and cross-validation errors. And this is the section where we're concluding, or subsection, where we're finalizing 6.1. What is 6.1? Is it something selection? Is it subset selection? 6.1 is subset selection, where we will take certain variables out. We won't include them in the model, usually because either there is no relationship between them and the response variable, or other variables do a better job of actually making predictions. We can do without some of the data in our or some of the data that's available to us. Right. Now, we're looking at adjustments, aren't we? Adjustments of what? In these different types of subset selection algorithms, the MK is picked on the basis of the RSS, or else the highest R squared. It's two different measurements, but I think they're kind of like equivalent to each other. Minimizing the RSS is the same as maximizing the R squared. But those are calculations based on the training data set, whereas really what we need over here is we would like the test mean square error. And this is what the book goes on to say when reading this bullet point. We can indirectly estimate test error by making an adjustment to the training error to account for the bias due to overfitting. Or else you could do it directly by using some kind of cross-validation, as what we had in the previous chapter. Now, the first one that we saw was CP. And what does CP stand for? well, it's just this one, right? It takes RSS, which is calculated on the training data set. And we had described it as a penalty last time around. It adds 2 times the number of predictors and the variance within the error terms. So the larger that variance and the more predictors you take, that counts against the CP. So the more predictors we use, the higher the value of D and the greater the CP, although the difference doesn't look too pronounced. There's a similar adjustment using AIC, a similar adjustment using BIC. And I think we can now look at estimating the test mean square error using the direct approach, which is basically cross-validation. Let's have a look. As an alternative to the approaches just discussed, we can directly estimate the test error using the validation set and cross-validation methods discussed in Chapter 5. We can compute the validation set error or the cross-validation error for each model under consideration. Each model under consideration, it's these M0, M1 up to MP, and then select the model for which the resulting estimated test error is smallest. This procedure has an advantage relative to these 4 metrics in that it provides a direct estimate of the test error and makes fewer assumptions about the true underlying model. It can also be used in a wider range of model selection tasks, even in cases where it is hard to pinpoint the model degrees of freedom. What do we mean by degrees of freedom? That's what we have in the parentheses over here, the number of predictors in the model, or hard to estimate the error variance sigma squared. In the past, performing cross-validation was computationally prohibitive for many problems with large P and or a large N. So traditionally, perhaps the AIC, BIC, CP, and adjusted R squared were more attractive approaches for choosing among a set of models. Of course, these days, computational power has come a long way. Nowadays, with fast computers, the computations required to perform cross-validation are hardly ever an issue. Thus, cross-validation is a very attractive approach for selecting from among a number of models under consideration. And really, this is just a lot of revision of Chapter 5. I think we can say that that section is completed to a high degree of completion. Let's move on to shrinkage methods. Let's remind ourselves there are 3 processes that we're considering in this chapter. We've just finished the section on subset selection. We're talking about model selection, right? There's now also shrinkage and dimension reduction. And we're starting from shrinkage right here. The subset selection methods described in the previous section involve using least squares to fit a linear model that contains a subset of the predictors. As an alternative, we can fit a model containing all P predictors using a technique that constrains or regularizes the coefficient estimates. These are those betas, or equivalently, that shrinks the coefficient estimates towards 0. It may not be immediately obvious why such a constraint should improve the fit, but it turns out that shrinking the coefficient estimates can significantly reduce their variance. And that's something we're trying to do, right, usually. Minimizing the variance and minimizing the bias. The two best known techniques for shrinking the regression coefficients towards zero are ridge regression and the lasso. So starting from ridge regression, and just before we do anything else, do we remember what the assumption is of linear regression? The assumption of linear regression, I'm going to change that negative into a positive, and just think of this as minus everything in the pink rectangle. So that will give you a negative B naught and your negative summation. The assumption in linear regression is that for any data subject I, think of a patient, think of a student, think of a company, you name it. With P characteristics, so every observation, we know these P characteristics for every observation, and that's from j equals 1 to P, then we are able to model, we're able to predict the response variable yi, and since it's a prediction, we emphasize that using this hat notation. The assumption is one of linearity. You estimate these betas. You also have an intercept term, beta naught. You could use these squares, for instance. You estimate the betas, and then you can kind of think of it as scalar products, right? You have a column vector of betas, a row vector of characteristics, and if you dot product them, you multiply the first beta with the first characteristic, and then you add onto that the second beta times the second characteristic. And how do we estimate those betas? Well, really the one method that we've seen so far is least squares. How does these squares work? The betas are chosen in such a way that they minimize the residual sum of squares. What is that? What's the difference? What's the difference between the actual and the expected squared, so that you don't have negative differences zeroizing with positive differences? And you sum each square, each residual squared, you sum it, which gives us the acronym, the residual sum of squares. And that's what we've been doing ever since chapter 3, if not earlier. Okay, so that explains that notation or that formulation. Ridge regression is very similar to least squares, except that the coefficients, okay, so this is the first time in this book, from what I remember, where we're discussing an alternative to least squares. So we now have ridge regression. Let's see. It's very similar to least squares, except that the coefficients are estimated by minimizing a slightly different quantity. In particular, the ridge regression coefficient estimates, beta hat, and we're distinguishing them. Let's highlight. We're distinguishing ridge regression betas from least squares betas by including the letter R. That R has nothing to do with R squared that we had earlier. I guess it's just R for ridge. And we select these by minimizing not the residual sum of squares, but instead we minimize the residual sum of squares plus, you see what this lambda is? Lambda times the sum of squared betas. Okay, where lambda, first of all, is non-negative, and it is what we're describing as a tuning parameter to be determined separately. And how are we going to determine lambda? Let's find my cursor. Equation 6.5 trades off two different criteria. As with least squares, ridge regression seeks coefficient estimates that fit the data well by making the RSS small. However, the second term, which includes lambda, called the shrinkage penalty, is small when beta 1 until beta p are close to 0, and so it has the effect of shrinking the estimates of beta j towards 0. Okay. The tuning parameter lambda serves to control the relative impact of these two terms on the regression coefficient estimates. When lambda is 0, the penalty term has no effect, and ridge regression will produce the least squares estimates. However, as lambda approaches infinity, the impact of the shrinkage penalty grows, and the ridge regression coefficient estimates will approach 0. Unlike least squares, which generates only one set of coefficient estimates, ridge regression will produce a different set of coefficient estimates, and now we're going to label them as beta hat, R, and lambda to emphasize the choice of lambda behind those betas for each value of lambda. Selecting a good value for lambda is critical. We defer this discussion to section 2.3, where we use cross-validation. Note that in 6.5, the shrinkage penalty is applied to the betas, but not the intercept beta naught. We want to shrink the estimated association of each variable with the response. However, we do not want to shrink the intercept, which is simply a measure of the mean value of the response when each characteristic is 0. If we assume that the variables, that is, the columns of the data matrix X, have been centered to have mean 0 before ridge regression is performed, then the estimated intercept will take that form. So what are we saying here? If we assume that the variables, that is, the columns of data matrix X have been centered to have mean 0. Okay, so you have imagine you have your data. Let's say we have 3 predictor variables. And it's saying that each column, the mean is saying that the mean of each column is 0. Yeah, so you could just like transform your data. You could transform your data here is what we're saying. And you transform your data so that the mean of each column is 0. Then in such case, beta naught would just be the average, the mean of the response variable. I don't think it's that important. Okay, an application to the credit data. In figure 6.4, figure 6.4 is this one. The ridge regression coefficient estimates for the credit data set are displayed. Where are they displayed? The ridge regression coefficients. In the left-hand panel, each curve corresponds to the ridge regression coefficient estimate for one of the 10 variables plotted as a function of lambda. Oh, okay. So each curve is one of the 4 variables in the credit data set. So we're saying is if you take lambda as 100, for instance, if lambda is 100, which betas are you going to take that minimize the... Did we even have a name for... Does this have a name? To minimize this, doesn't seem to have given it a name yet. But to minimize the previous expression's output, if lambda is 100, then it gives you this beta. It gives you so this beta over here, this would be beta limit. Limit is just one of the fields in the credit data set. Beta rating would be the same. Then you have beta student, which is 100, and beta income, which is negative 100. For that particular choice of lambda, notice that as lambda gets larger, oh, by the way, this is a log scale. So this is 1, this is lambda's 1, this is lambda's 10, this is lambda's 100, lambda 1,000, and lambda 10,000. A log scale is useful just to get just to include more orders of magnitude when you're just displaying data. For example, the back solid line represents the ridge regression estimate for the income coefficient as lambda is varied. At the extreme left-hand side of the plot, lambda is essentially 0. And so the corresponding ridge coefficient estimates are the same as the usual least squares estimates. But as lambda increases, the ridge coefficient estimates shrink towards 0. Excuse me. When they said left-hand side, I was looking at the wrong, this left-hand side. So when lambda is basically 0, these four values are the four betas that you would get from least squares regression. But as you increase lambda, they're going to become smaller and smaller and smaller. Now, why we're doing this, we haven't seen yet, and I don't have the answer to that question. But apparently there are certain advantages doing it this way. So in the plot, the income limit, rating, and student variables are displayed in distinct colors, since these variables tend to have by far the largest coefficient estimates. While the ridge coefficient estimates tend to decrease in aggregate as lambda increases, individual coefficients such as rating and income may occasionally increase as lambda increases. Rating and income. So there are points where I actually don't know. What are we saying here? While the ridge coefficient estimates tend to decrease in aggregate, rating and income may occasionally increase. So you see rating, it increases like this. So it does increase over here. And I mean, the black is increasing, but you need to look at the distance from zero. So in terms of its absolute value, the black is getting less and less, but then it does increase a little bit over here, but then it goes back to approaching zero. The right-hand panel of figure 6.4 displays the same ridge coefficient estimates as the left-hand panel, but instead of displaying lambda on the x-axis, we now display this thing over here. This thing over here. And we're going to see what this is. But we're still looking at standardized coefficients against as the vertical axis. Now what is this? As I don't know, might be new notation for most of you, but it's actually very similar. Do you remember at A level when we would calculate the magnitude of a vector? Wasn't it Pythagoras' theorem? And it's basically that. So basically what? It is basically if you have a vector, think of beta. We're not using bold. The book rarely uses bold for vectors. But if you have a vector beta, then you square each coefficient, add them, square root, and that gives you this. That's always going to be a non-negative real number. So let's read it. The notation. This is known as the L2 norm. Norm is just you're like measuring with a ruler, and in mathematics there are many different ways of measuring a distance. But this is the distance that the type of distance calculation that we're most familiar with, going way back to secondary school, and the very often the distance that we use, very often the distance calculation that we use in real life. So there are many different types of norms. This subscript is just saying use the L2 norm, standard notation. You'll be doing this in, those of you who have statistics in second year, you'll be doing this in non-linear optimization problems. Who knows, maybe even do it in first year. So it's pronounced L2. of a vector and is defined as this. It measures the distance of beta from 0. As lambda increases, the L2 of this will always decrease. Okay. And so will this over here. Now notice that what's going on is you first calculate the denominator by using least squares. You start with, to get this second chart. I do apologize for yawning so frequently. I am quite tired today. You start with these squares. So what is these squares? It minimizes the residual sum of squares, and it gives you all those beta hats. So you have a vector of betas, or beta hats rather, and you calculate the norm, and we should be more specific, the L2 norm of that vector. So that's going to be your denominator. Now, for every value of lambda, you perform ridge regression, and you can calculate this over here. As lambda increases, the L2 norm, so the denominator, the numerator will always decrease. So have we just flipped these around? What do I mean? As this increases, this will actually decrease. So I think that's why this curve starts like this and goes up. But if you look at this chart, it's kind of doing the exact opposite thing. It's doing this. Same thing here. The red goes like this, but over here, you're going to look at it like this. So it's the same thing. The only difference is that this instead of looking at lambda, you're looking at the kind of getting an idea of the beta values over here. It is a bit of a dry topic so far. Let's see, but let's not get discouraged. There are times where we do skip sections, and we may choose to actually skip parts of this section, but I'd like to get a few more pages in. The latter quantity ranges from 1 when lambda 0, right? Do we remember this? When lambda 0, ridge regression is just the same as least squares when lambda 0. So these two would be equal. You'd be calculating the same beta. You'd get the same betas from least squares and ridge regression, and that gives you 1. So that's the largest possible value. Largest possible value is 1, just like the smallest possible value is 0. So the smallest possible value of lambda is 0. The largest possible value of this expression is 1. And when lambda is infinity, you get it approaching to 0. Therefore, we can think of the x-axis in the right-hand panel. This is the right-hand panel. The x-axis in the right-hand panel of figure 6.4 as the amount that the ridge regression coefficient estimates have been shrunken. That's the name of the method, right? Shrinkage towards 0. A small value indicates that they have been shrunken very close to 0. The standard least squares coefficient estimates discussed in chapter 3 are scale invariant. Now, invariant means something that doesn't change. Usually, let's see, multiplying xj by a constant c simply leads to a scaling of the least squares coefficient estimates by a factor of 1 all over c. In other words, regardless of how the jth predictor is scaled, xj times beta hat j will remain the same. So the way least squares regression works, if you have an input data, and for some reason, don't ask me what that reason is, you choose to transform the data. So you have everyone's age, and you say, okay, I'm going to multiply, but before I give the model the data, I'm going to multiply everyone's age by 20. What that would do is it would get the beta and actually multiply it in the opposite direction so it would divide it by c. So then when you come to calculate y, the contribution towards y of the jth predictor variable, the c times 1 on c, those will cancel. Now, in contrast, the ridge regression coefficient estimates can change substantially when multiplying a given predictor by a constant. For instance, consider the income variable, which is measured in dollars. One could reasonably have measured income in thousands of dollars, which would result in a reduction in the observed values of income by a factor of 1,000, right? So if you choose to measure in thousands of dollars, your data, your new data is now division by 1,000. The income data. Now, due to the sum of squared coefficients term in the ridge regression formulation, such a change in scale will not simply cause the ridge coefficient estimate for income to change by a factor of 1,000. So if we were using linear regression, that's all that would happen. The relevant beta, the beta income, would just decrease by a factor of 1,000 to, would increase, right? I hope you're catching out these mistakes. If of mistakes when I misspeak, if I had a data set, but then I choose, actually, let me quote the income values in thousands. So I've taken that data set and I've actually changed it to a new data set by dividing each income figure by 1,000. Now, what would happen is that if you perform linear regression using these squares, what you would get is the beta would increase by a factor of 1,000. Now, that would be if it was least squares. However, since we're using ridge regression, where's my cursor? This figure, which you would compute when estimating y, will depend not only on the value of lambda, but also on the scaling of the jth predictor. In fact, the values of xj times beta hat j lambda may even depend on the scaling of other predictors. Therefore, it is best to apply ridge regression after, and we have this idea of standardizing the predictors. And what does it mean to standardize the predictor? You take your raw data and you're going to turn it into a standardized I don't know, input data value. How? Well, for each, let's have a look. We are looking at xij. What does xij mean? Is that the ith observation and the jth? Yeah, it's the ith observation. So, for example, the 100th observation and the jth field. I don't know, not number of daily study hours. And what do? We calculate the mean. Now, what is that? That must be the mean within a single column of data. So that's the mean of all observations, the mean number of daily hours of studying. You subtract it from each observation's reading. You square, you sum. So this is like a standard deviation. We've never really, I mean, we've mentioned standard deviation quite a bit, but we've never really given any explicit formulae. So the denominator, once you square root, this gives you what we've occasionally referred to as the standard deviation. So you get an idea of the variability within a specific predictor variable. So the number of hours studied. Yeah, how many teachers one has, you name it. And then each observation's xj. So for every observation I, you take its xij and you divide it by, we're transforming the data over here, and you divide it by what I'm referring to as, or what we usually refer to as, the standard deviation, so that they are all on the same scale. Yeah. Yeah, this is called standardizing, and if you're doing, you may have done the normal distribution elsewhere. If a random variable has this normal distribution, you may standardize it. You've probably done this. You may standard it. It's very much the same. It's very much the same concept. Like this, you can sort of compare like with like. You standardize, so then instead of apples and oranges, you're comparing apples to apples. In 6.6, the denominator is the estimated standard deviation of the jth predictor. Consequently, all of the standardized predictors, so from the predictors you get the standardized predictors, and they will all have a standard deviation of 1. As a result, the final fit will not depend on the scale on which the predictors are measured. So having said all this, what's the point? The point is that we don't want our results to depend on if I've chosen to measure in thousands or not, if I've chosen to measure in kilograms or in pounds, for instance. And we get this by first standardizing. In figure 6.4, it's probably next page. No. Figure 6.4 is what we were looking at earlier. The y-axis displays the standardized ridge regression coefficient estimates. Okay. So these are the ridge regression betas, but they are the standardized betas. So what does that mean? It means the coefficient estimates that result from performing ridge regression using standardized predictors. Now, and this is what we're all asking, right? Why does ridge regression improve over least squares? Ridge regression's advantage over least squares is rooted in the bias variance trade-off. As lambda increases, the flexibility of the ridge regression fit decreases, leading to decreased variance but increased bias. It's always that trade-off, right? You decrease one, you increase the other, and squared bias is black and variance is green. And then we have purple is the test mean squared error. I mean, can we just think of it as addition? It's not quite addition, but you're getting the purple from combining in some way the green and the black. And this is where you get the lowest mean square error. Let's read the explanation. Squared bias is in black, variance is in green, and test mean squared error is in purple for the ridge regression predictions on a simulated data set, which is what enables us to speak of test mean squared error. If the data set isn't simulated, what does simulated mean? That you know the parameters in advance, which is the exact opposite of the real life situations that we'll be working with in future. And we have these two charts, both as a function of lambda and as a function of this expression. The purple crosses indicate the ridge regression models for which the MSE is smallest. Okay. This is illustrated in the left-hand panel of figure 6.5 using a simulated dataset containing P equals 45 predictors and N equals 50 observations. As always, we like the situation where we have P less than N. So 50 observations, think of them as, for example, 50 life policies sold by a life insurance company. And we're trying to predict how long a person will live based on, or at least we have the information of, we have data relating to 45 characteristics of these individuals. If they're into extreme sports, smoker, non-smoker, family medical history, what their occupation is, where they live, any what's the word? when it's pre. I don't know. My brain is freezing. Anyway, you hopefully those examples give you an idea. The green curve in the left-hand panel of figure 6.5 displays the variance of the ridge regression predictors as a function of lambda as the least squares coefficient at the least squares coefficient estimates, which correspond to ridge regression with lambda equals 0. The variance is high, but there is no bias. Interesting. So these points are least squares, right? It's when lambda is 0. The bias is 0. Why? Is that something we're meant to know? The bias is 0. Is it always is it the feature of these squares that I don't know, I'm afraid. But as lambda increases, the shrinkage of the ridge coefficient estimates leads to a substantial reduction in the variance of the predictions at the expense of a slight increase in bias. Recall that the test mean square error, plotted in purple, is a function of the variance together with the square bias. For values of lambda up to about 10, the variance decreases rapidly with very little increase in bias, which is normally what you want. Although there is a trade-off, and it's not an equal trade-off. Increasing, or let's just put it this way, decreasing variance doesn't necessarily increase bias by the same proportion. Consequently, the mean square error drops considerably as lambda increases from 0 to 10. Beyond this point, the decrease in variance due to increasing lambda slows, and the shrinkage on the coefficients causes them to be significantly underestimated, resulting in a large increase in the bias. The minimum mean squared error is achieved at approximately lambda equals 30. So this is lambda equals 30. Why? This is 10. This is 1,000. I can't be right. Is that only 30? Well, it's a log scale. So yeah. Yeah. So this is 100. This is 1,000. But the middle between them is not the mean of 100 and 1,000. So yeah, lambda is around 30 over here. Interestingly, because of its high variance, the mean squared error associated with the least squares fit when lambda is equal to 0 is almost as high as that of the null model for which all coefficient estimates are 0. Oh, interesting. When lambda is 0, it's never really occurred to me. When lambda is 0, when lambda is infinity, excuse me, when lambda is infinity, didn't we see that your betas get closer and closer to 0? Well, at infinity, now, of course, you never hit infinity, but at infinity, they will be exactly 0. And that's the null model, isn't it? If your betas are 0, then this is just 0. And it's like you don't have any predictor variables in the first place. And apparently the observation is that this mean square error, okay, it's saying it's, well, let me because of its high variance, the mean square error associated with the least squares fit when lambda is equal to 0 is almost as high as that of the null model, for which all coefficient estimates are 0. Remember what the null model is. The null model, you're not even using any of your data when lambda is equal to infinity. However, for an intermediate value of lambda, the mean squared error is considerably lower. So you get that around 35 as opposed to 50 for the least squares model and around 60 for the null model. The right-hand panel of figure 6.5 displays the same curves as the left-hand panel, this time plotted against the L2 norm of the ridge regression coefficient estimates divided by the L2 of the least squares coefficient estimates. In general, in situations where the relationship between the response and the predictors is close to linear, the least squares estimates will have a low bias, but may have high variance. Now this is where I think we have explained this before, but every time I see a sentence like this, had I only seen the first half and I was asked to complete it, in general, let me read again from the beginning of the paragraph. In general, in situations where the relationship, this means the true relationship, okay, between the response and the predictors, so between the y and the x's, is close to linear, so meaning, in other words, that we have a good, that the assumption, it's a safe assumption, you know, that the linear regression is the assumption of linearity makes sense, is a valid one. The least squares estimates will have low bias. And what do we mean by bias? I'm not entirely sure. But bias is when, oh yeah, so if it's a very flexible model, if there's overfitting, that's high bias. That's high bias. Whereas you have low bias when it's something that, yes, something which is less flexible. Okay, yeah, so that is the case, right? If it's a linear model, your bias is quite low because if you think of it as fitting a curve, it's not doing its best to follow the data on sort of like an individual data point basis, but may have high variance. And when you have high variance, I think that's just the epsilon error term. Okay, well, it's actually going to expand now. This means that a small change in the training data can cause a large change in the least squares coefficient estimates. Really, I would have thought that would be if we had high bias, that a small change. Oh no, this is high variance because it's a small change in the training data, not to one data point. Like you change the training data can cause a large change in least squares coefficient estimates. In particular, when the number of variables p is almost as large as the number of observations n, as in our example, the least squares estimates will be extremely variable. And then it gets even worse. If p is greater than n, then the least squares estimates do not have a unique solution, whereas ridge regression can still perform well by trading off a small increase in bias for a large decrease in variance. Hence, ridge regression works best for situations where the least squares estimates have high variance. So this is really where you would use ridge regression, where you have high variance, where the least squares estimates have high. So where the betas, do you remember we had calculated the standard error SE of each beta? That was when we were doing the null hypothesis, where we were talking about p-values. Let me continue reading. Ridge regression also has substantial computational advantages over best subset selection. Do you remember best subset selection? It's where Pascal's triangle, you look at literally every combination of predictors, using some of them and leaving others out, searching through 2 to the p models. As we discussed previously, even for moderate values of p, such a search can be computationally infeasible. In contrast, for any fixed value of lambda, ridge regression only fits a single model, and the model fitting procedure can be performed quite quickly. In fact, one can show that the computations required to solve 6.5 simultaneously for all values of lambda are almost identical to those for fitting a model using least squares. Okay, so we kind of rushed this last part. I do realize this, but at least we got these 4 pages of ridge regression done. Maybe we'll do a quick recap tomorrow evening, and then we'll move on to the lasso, which is another type of what we're doing over here of shrinkage. So look, in lasso again, there's this shrinking the coefficients to 0 or towards 0. Notice that we don't have 2 anymore over here. So we're going to use a different type of, think of it as a ruler, a different type of distance, where I guess we'll explain it somewhere. Okay, but that's it. That's it for today, and we can stop over here.